plus da 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 plus the absolute value of xn for x equal to like x1 v1 xn vn. So we can define a norm like that. All right, so I'm just saying, for the purpose of the proof part of the course here, let's assume that we've constructed, so let's say this. If the vector space you're given doesn't already have this property, then we're going to replace the norm that we're given with this norm that we can construct over the basis. And then this clearly has the property that the this is greater than or equal to any particular absolute value by construction, right? All right. Okay, so then what? Well, we have, and I've been saying everything about V that I should have been talking about where. Because where are we actually doing this? Not in the domain. Where I actually need to make this step, it's in the codomain. It's in the range, right? I mean, so then f of x minus L is equal to the sum I equals 1 to m of f sub I of x minus L sub I times wi, right? Hence, the absolute value of f(ix) minus L sub I is less than or equal to the norm of f of x minus L, which is less than epsilon. Well, voila. We've just shown that we can make the absolute value of the component, the ith component function, within epsilon units of the limiting value L sub I. So this implies, what's this tell me? This tells me that the limit as x goes to x naught of f of x, f sub I of x, is equal to L sub I for all I. That's the end of the forward implication. I think I have a proof. I have a proof which doesn't use this norm trick that I just did, but man, it was complicated. It was nasty. And I forget what I did. This is a better way, I think, because it's easy. And so the other way, assume the limit as x goes to x naught of f sub I of x is equal to L sub I for all I equals 1 to da 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 m. And then let epsilon be greater than 0. Choose delta sub I greater than 0, for which 0 less than norm of x minus x naught less than delta sub I implies the absolute value of f sub I of x minus L sub I is less than what?
Less than epsilon?
No. So here you're going to want a, in 2 dimensions, we did epsilon over 2.
Over, yeah.
And now we want epsilon over m, right? So then we construct L as equal to the sum I equals 1 to m of L sub I, W sub I, and delta equal to the minimum of delta 1 through delta m, right? And suppose that, 0 is less than norm of x minus x naught is less than delta. And then we study the norm of f of x minus L. In particular, we study f of x minus L. All right, so that's straight up, I'll write it out here, the sum, right, I equals 1 to m, And I'm going to do my calculations all at once here. F of x sub I minus L sub I, right, times Wi. Oof. I see at this point. There's another assumption I should have made. What's the other assumption I should have made? And I want the norm of V sub I equal to now this is a less critical assumption, but if we bake this into the cake at yeah, 1. If we make it 1, then that will declutter certain other things. Like we're about to find that that's an assumption of our construction in the converse direction already. It's about to see what see. So then triangle inequality, right? This is less than or equal to the sum I equals 1 to m of the absolute value of f sub I of x minus L sub I times the norm of Wi. You see, it's not a big deal, but if I wasn't going to operate under the assumption that the norm of the basis was 1, in other words, if I wasn't going to operate under the assumption that I'm working with a normalized, a normal basis, I don't really want to say orthonormal because I'm not assuming that there is an inner product here, okay? So I don't even know if orthogonal has meaning in general for these examples. But certainly length 1, if that has length 1, well then this is just equal to 1, and this is less than or equal to, well it's just less than because they're all strict inequalities, right? The sum I equals 1 to m of epsilon over m, which is also known as epsilon. So if we weren't working with the normalized basis, it's easy enough to repair this proof. That's not a hard thing. We would just do what? We would just dress this up with division by the norm of Wi, and we could easily adapt this proof to that. All right. So there you go. This is the vector limit theorem. It says anytime we have a mapping of finite dimensional vector spaces, the limit exists if and only if the limit of every component function exists. So this we use. With this in hand, it becomes pretty easy to prove the product rule that we were talking about once you set things up the right way. So I guess that's probably a good place for us to stop. Let me see if I've given you your fair share for today. We're still got I haven't quite talked that long. Still got 7 minutes. Let me, so I try to do an hour and 15, right? Let's see here, what should we do next? How about, you know what? We'll just stop here because everything I can think of is more than 8 minutes of work. So anyway, thanks guys.